the circuit. So we have a oscillator, produces a sinusoidal current going through a resistor, inductor, and capacitor. This is running at a particular omega. If you're given the frequency f in hertz, this omega is equal to 2 pi times that frequency f in hertz. So if you're talking about outlet, a wall outlet, this frequency is 60 hertz. So you take 2 pi times that 60 hertz if you're dealing with something that's coming from a wall outlet, because that's delivered in. And you're given a voltage here, but the voltage you're given is generally the RMS voltage. And so remember, for all of our RMS voltages that we have, for all the RMS voltages that we're talking about, it's equal to the maximum voltage, I'll just say V naught here for some kind of maximum, divided by what?
Square root of 2.
Square root of 2. And I don't care what it is. I don't care what it is, any sinusoidal function thing. In other words, if I had apples growing on trees in a sinusoidal function, so I have apples growing on trees, sinusoidal function. Okay, apple equals apple naught times some sine function. Okay, I don't care if I want the RMS value of apples. It's equal to this divided by the square root of 2. There you go, see? I don't care what it is, sinusoidal function, the RMS values, the maximum divided by the square root of 2. You did not have to write notes about the apple. That will not be on the final answers. But you need to understand that all of these values, can be related to each other. And just like that phasor diagram that we drew last time. So we drew a phasor diagram looking at the voltages. So we looked at and all of these values are going to pertain to the RMS value. So we drew a little phasor diagram. And we basically said the phase of the current we put along the x-axis. Now theoretically you don't have to, you could think of the current as having some phase and that this thing kind of spins around in a counterclockwise fashion. Kind of like you could take each one of these arrows that I draw and kind of spin it like this, because they're all going to be in a certain phase. And then that phase continually goes around. The reason why I draw it like this is this particular orientation. It makes it simpler in order to calculate things and to see what's going on. Okay, but really what's going on is happening is that is going around and around, and they're all changing phases as they go. So we have the current, which we're going to put along this x-axis here. So when we're talking about the current, we're talking about that voltage across the resistor. That's right in phase with that current. The voltage across the inductor is 90 degrees ahead of the current. The voltage across the capacitor is 90 degrees behind it. 90 degrees behind it. And so when we solve for this, we want to solve for the total voltage. We want to see that what the total voltage is with respect to the current. The total RMS voltage would add up with these things like vectors. And yes, it is actually true that the voltage across the inductor, the voltage you have across the inductor, is directly out of phase with the voltage across the capacitor. So in other words, when the inductor voltage is a positive voltage, the capacitor voltage is a negative one, and vice versa. Okay? So in this case here, notice that I did this. So this would be still the absolute value of VL minus VC. And then this is your total RMS voltage right here. I'll put VT there. V total. Yes?
I noticed that you had your V total position clockwise last time. Is that because you could, in a different RLC circuit, have a higher and or a lower value of VC and VL?
Oh, yeah.
Depending on the components?
Yeah, yeah, somebody asked me that last time, so was there any particular reason why I drew the one longer than the other? So today I drew it the other way. I said, okay, this time we're going to have it in such a way, VC. Because remember, these voltages here, these things are adjustable. So in other words, at low frequencies, this one's going to be bigger.
Oh, regardless of the components, you adjust the frequency and one rises and one falls.
Right.
Okay.
As you adjust the frequency, because absolute value of VL minus VC, because when I do this, this error is this size.
But wouldn't it be going north because it's absolute value?
No, the vector's this way. I'm just drawing this to show you the size of it. The size of it is absolute value of VL minus VC, right? Which in this case is a negative number. In other words, this is going to work no matter whether it's positive or negative. Okay. However, it doesn't matter because when you go to calculate this, you square the thing anyway, so it doesn't matter. So in other words, what your V total turns out to be is the square root of VR squared plus, you have to be careful about this, VL minus VC quantity squared. Okay, well now let's take our diagram, and instead of, we're going to divide every term here by the RMS current in the circuit. Yes?
Is that 1/2 at the end?
No, that's squared here, and it's under a square root.
Okay.
In other words, it's the vector sum of the two. This side squared plus this side squared square root.
You should really coordinate with the labs. We did this lab last week.
Well, the good, you
2
should be
weeks
doing
ago.
great.
It didn't make sense. I was just filling in.
Well, I mean, in here,
Yeah.
this homework should be like nothing.
Yeah.
Okay. It always happens. It happens that's why there's a big long explanation in your lab book of what it comes from. You can go back and read it. I wrote it. Please go read it. Okay? Actually, I did write that one. The one where it talks about the frequency variance. That's the one I wrote.
Editing comments to you?
Actually, they did give me editing, credit on some of these things too.
Oh no, I found misspelling.
Oh, that one too? Yeah, hey. How long ago did I do that? 2007, 2008, somewhere around in there I did it. And I did it with somebody else, and there's some of the labs that they did and I edited it, and the guy that's redoing it now, there's somebody actually redoing the 220B lab manual. So I don't like this, I don't like this, I don't like this. I kind of warmed up to this is okay, and this is all right. So they're redoing it again, and it happens, it happens. It's every time you get an iteration of it, we might correct some misspellings and then misspell a couple of other things. So that's just happens every time. All right, so what I'm going to do with this is I'm going to take this and divide every term by the by the RMS current. So if we divide all these voltages by the RMS currents, remember how we got those voltages. Those voltages came from that reactance. So in terms of the RMS voltages here, if I divide those by the RMS currents, I'm going to get a chart of reactances. And it's going to look very similar to this. Okay? So we're going to draw our axis again. And once again, we're going to say that the current is going along here, even though these the reactances themselves don't have a phase, their corresponding circuit elements do. Their corresponding circuit elements do. So when I draw this, I'm going to draw out here, and this is the phasor diagram that we generally use. We draw the resistance out this way, because that's the V sub R divided by the RMS current. If I were to divide the VL by the RMS current, what would I get? What do we define that thing as? Microsoft. No, perhaps Excel. Microsoft Excel, see? Yeah, the reactance. So remember when we defined each of these, we said that VR was just the RMS current times the resistance. There is no reactance with that. If we did call a reactance, we'd say it's the resistance itself. But for the other two, we defined this reactance we defined that reactance because they're not really resistors, so we defined this term called reactance that kind of acts like a resistance for an AC circuit. Okay, so up here, I'll make the L bigger this time. Okay, so we have XL and we have XC. And now we want to add these up. We can add these up like we did the other ones. So here we have the quantity, which is the absolute value of XL minus XC. And in this case, of course, I drew it for a different RLC circuit because I've made the XL be larger than the XC. So
But this can also go the other way.
it can also go the other way.
Does that depend on the frequency as well?
Oh yeah, you'll see how this works. Okay, so we do this, okay? And now what we do is we talk about this as being the total impedance of the circuit. So we have a new letter and we call it Z, capital letter Z. This is the total impedance in your circuit. And so Z is equal to the square root of R squared plus quantity X sub L minus X sub C quantity squared. Anything squared. And of course, we then also will define our phase phi. So this phi is actually calculated with either the voltages or the reactances. The tangent of the angle phi is equal to XL minus XC divided by R. Now notice in this case when we're talking about the tangent, or we're talking about this phase angle, we do not put absolute values here. We do not put absolute values here because it does have meaning which one of these is larger. It's the reactance of the capacitor or the reactance of the inductor.
Wait, we didn't have absolute values in the tan?
You don't have absolute values in the tan. You really don't have absolute values here. You're squaring it, so it doesn't matter.
Right. Did we have it in the...
No, I just put it in a diagram.
Right.
That's the only place
So
where
it's
it's
the same situation.
Same situation. Okay.
The reactance.
Yeah. All right. Now, just to let you know, if any of the circuit elements are missing, if any circuit element is missing, then that quantity, that reactance is 0. Put that reactance in as 0. So if there's no inductor, X sub L is equal to 0. If there's no capacitor, X sub C will be equal to 0. There never really will be no resistance. The resistance can be really small, but there will be can't really be no resistance in here. So we're going to deal with a little bit more realistic situation here. We're not going to give you, we might give you a small resistance and say that this is a small resistance with an L, just an L and C, but there always will be some. There always has to be some.
Yeah. I was thinking about if there's no inductor
Mhm.
on the square root, would you keep the minus sign? But it doesn't matter because you have a square.
See, what happens is it's negative SC squared. This is where people make algebraic mistakes here. If you have no inductor, the negative sign gets squared. In other words, I have a capacitor there. It is going to add, you're not going to have anything, because otherwise in that, what you do is you have the frequency low enough and then this would subtract and I'd have an imaginary
Okay. And then in the case that you're trying to find V, are you keeping negative XC?
Yeah, keep the negative. Keep the negative. Yeah, always keep the negative in. Because it's minus. All right, so. All right, let's take a look at the circuit. Let's just do one of these, okay? Find the total impedance of the circuit. All right, so. Okay, so I have a 20, let's make it 200. 200 ohm resistor, series with a 4 millihenry inductor, capacitor, we'll make it 200 microfarads, and I'm running my circuit at a RMS voltage of 110 volts and a frequency f of 60 hertz. In other words, what would happen if I took this stuff and stuck it into an outlet? You know, put these things, just plugged it into an outlet. Let's see what happens, okay? So a few things I want to find in this case. I want to find the total impedance in the circuit. I want to find the RMS current in the circuit. And I want to find my phase angle. Phase angle phi. Okay, so let's get the total impedance of the circuit. Well, the first thing I need to do is I need to calculate my X sub L and X sub C. They do give you a formula in the book which combines all this stuff. So let me show you what it looks like. It's just really strange where you're trying to plug in those numbers there. My suggestion is just calculate the reactances separately and then do it that way. So it makes it a little simpler. Especially since if there's no capacitor in the circuit, you might be tempted to put 0 in for the capacitance, which would blow this thing up. So you can't do that, okay? So that, it's the reactance that's 0. You don't plug in 0 for the, yes, all right. So let's, okay, well, how about the resistance? What's it? Good, 200 ohms. That's just, the resistance is just 200 ohms. 200 ohms. It is what it is. Okay, that's the one that is what it is. These other ones aren't. All right, so the reactance of the inductor is equal to omega times L. Now let's go ahead and calculate our omega. Omega is 2 pi times 60. So what do we get for our omega? Don't 120 pi me. Give me a number.
I'm still getting it right.
376.
Okay.
499.
377. Actually, could have written that down. Actually, had remembered that. I just wanted to make sure I remembered that. It's because it's used so much because it just your outlet. Angular frequency, 60 hertz, yeah. Okay, so this is 377 times 0.004. So what's the reactance of my inductor?
Um,
1.33?
1.51.
Okay. I'll just say 1.33.
Oh, 51.
Huh?
He said 51.
51.1, okay.
No, 1.51.
Dang. 1.51. 33 never came in.
There we go.
Perfect.
All right, units.
Henry over second.
Ohms.
Oh.
These are all like resistances.
It's technically Henry over second.
No, it's technically ohms. It needs to make sense to people. All right? X sub C. Okay? This is 1 over omega C. So it's 1 divided by, let's see, omega is 377. And the capacitance is 200 times 10 to the negative 6. This one's not going to be very much either, is it?
It's 13.26.
13.26? Units of that? Ohms, okay? All right, so let's use a smaller resistor. There we go. There we go. I need to make up my numbers better. Sorry, I just wiped out. The reason why is that I wanted this to be comparable to these, and right now it's not. You know, it's 13. These are small. In 200, this is small. You put that square root in there, you're basically going to get 200. In other words, the inductor and the capacitor aren't going to do squat, okay? Because the frequency is wrong for it to happen. All right, so. All right, here we go. So now let's calculate our impedance. So Z equals the square root.
On this question, what's the question? What are we looking for?
We're looking for the impedance, we're looking for the RMS current, we're looking for the phase. Those three kind of standard things we can ask. Plus, XL is 1.51 minus X sub C, 13.26 squared. Well, somebody calculate that number and tell me what you get. That stupid alarm.
23.2.
Okay, 23.2. Okay. 23.2 ohms. So the RMS current is our RMS voltage divided by 23.2 ohms. .74 units for this. And let's look at the phase angle. Tangent of phi is equal to XL, which is 1.51, minus X sub C, 13.26, divided by the resistance, which is 20. So somebody calculate that number, take the inverse tangent, and tell me what you get. Huh?
I'm just gonna tell what the notes.
-30.43.
Okay, negative 30.43. Two of these.
So we use the impedance to get that.
No,
current.
you use these.
The current.
Yes, use the impedance because in terms of the total RMS voltage is equal to the RMS current multiplied by the impedance.
Does your P value imply the total impedance is 30 degrees clockwise from your resistance? How do I interpret that?
All right, let's interpret this. Okay, so in terms of this phi, we think of this thing as rotating counterclockwise like this. In other words, going toward positive value of the angle. So for phi values that are positive, phi greater than 0, phi values that are positive, greater than 0, the ones up here. The voltage would be in here, the current is here. So what we would say is we would say that the voltage leads the current. The voltage leads the current. In other words, the voltage is ahead of the current. The voltage will peak first, then the current peaks. So if I looked at the two waves of the voltage and the current, the voltage is going to peak first, then the current peaks. Your wave goes in this way. So the voltage peak first, then the current. Okay? If the phi value, and this is what, and in this circuit, we also would refer to it as an inductive circuit. We refer to that as an inductive circuit. And the reason why we refer to it as an inductive circuit is because that means that the inductor in the circuit is dominating this thing in terms of the phase. In other words, I could create the same circuit if I just had an inductor change the values. I wouldn't really need the capacitor there, because I can get a positive phi with an inductor by itself. Everybody see that? I don't need a capacitor to get it. Phi less than 0. Okay. We could say this one of two ways. The voltage, I'm going to write it like this, lags the current. You could also say the current leads the voltage. It's just leads one lag. Here the voltage lags the current. The voltage is behind the current. The voltage is going to peak after the current does. Since we can create a circuit like this without using an inductor, and all I would need is a capacitor to do it. In other words, I cannot create this circuit with a capacitor by itself, because capacitor is always going to be behind. The capacitor is always going to drag the voltage behind. And I can't create this type of circuit with just an inductor, because the inductor is always going to push the voltage ahead. Okay. And this is a capacitor. What I refer to as a capacitor circuit. So there's our phi, there's this, okay? And sometimes the capacitor is bigger, and sometimes the reactance of the capacitor is bigger. And in this case, and that's what happened in this case here, the reactance of the capacitor is bigger. By the way, if I lowered the frequency more and more here, by the way, if I used the frequency that was, say, 10 times less, then this capacitive reactance would be 130 ohms. And you would find that this number wouldn't even be close to the resistance anymore, because it would start getting dominated by that capacitor. So in terms of what we look at with the way that the current works in this circuit, if I have this frequency just so happen to be kind of near where these two were both kind of low and complementary to this, but if I were to have decreased the frequency by a factor of 10, then this would increase by a factor of 10. The capacitance would. I could do it the other way too. Let's say that I increased the frequency by a factor of 10. Then this would increase by a factor of 10, and this would be 15.1. This would decrease by a factor of 10. This would be 1.3. Oh, because I'm pointing right here. Oh, sorry, there we go. All right. So in other words, here's my x sub c. This is my x sub c right here. And this is my x sub l. And those are adjustable. I mean, not if you put it in the wall, because you're getting things out of the fence. But if you have a power source that you can adjust the frequency on, then here you go. You can adjust the frequency until you get a desirable reactance. More on that in a minute. We're almost there. Scoop step. No, because then you can't see this. Oh, I'll zoom in. Jeez, like blank if you do and blank if you don't, I swear. You know about everything. All right, now we'll go take a look at power in an RLC circuit.
So this would be like the first example where it goes.
Mm-hmm. in an AC circuit. Well, if you want the average power output into a general AC circuit, if you recall, for a pure resistor, it's 1/2 multiplied by, so for a pure resistor, the power is 1/2 multiplied by the current squared multiplied by the resistance R. That's the power output of a pure resistor. Now what we could do is for this circuit here, we can talk about the average power. And if we take a look at the pure resistance, the average power output, how we defined it, that's the RMS current squared multiplied by the resistance R. Well, this RMS squared divided by 2, okay, this is just the current maximum squared, 5 by 2. If I plug that in, I can substitute this and say this is the voltage RMS squared divided by the resistance R. Or, the other way to put it, whoops, I'm sorry. Or the VRMS multiplied by the RMS. There's no half here.
So just
There's a half there because this includes the half in it. This includes the half in it because if I take this divided by the square root of 2, divided by the square root of 2, I squared it, so I overcounted my halves. Because when I place RMS, I differ. Yeah. All right, here we go. So they kind of go through each one of these things, which I think is kind of silly. Doesn't make any sense, when I go through the whole thing. But what you want to do is you can put it in terms of you can put this in terms of what's going on in the circuit itself. When you have an AC circuit, and this is a pure resistor. These are for pure resistors. You don't get this full power output. You don't get the full power output of it because they're all out of phase with each other, and this is the voltage is out of phase with the current. And so you don't get this nice thing. So in other words, this would be the value if they both were in phase with each other for a pure resistor circuit. For something that's not a pure resistor circuit, your average power output is changed by a factor of the cosine of the phase angle phi. In other words, your power in your AC circuit depends on how it gets interfered with by your inductor and your capacitor to your power output. Because the voltage and the current aren't in phase with each other. There's that factor of cosine of phi that's keeping them out of phase. That's consistent throughout the whole cycle, so therefore that factor comes in here. So this is your power in an AC circuit. I don't know why they took 2 pages to get to that. I should have just gave you that in the first place, so it doesn't make any sense to me. Don't mind. There's all right, here we go. Go back to where we've been. L. And we have an impedance that goes along with it. these two. Take a look at these two things. As a function of frequency. Okay? So what I'm going to have is I'm going to draw a little graph here. It's my reactance as a function of frequency. Now x sub c, recall that x sub c is 1 over omega c. So it's a 1 over omega function. So it looks like this. Okay. And it would approach 0 at infinity, and it approaches logarithmically. So at very low numbers, it's high reactance. At very high numbers, it's low. Okay? X sub L is this, omega L. What's it going to look like on this graph? It's going to be a straight line. It's going to be a straight line. In other words, at 0 frequency, there would be no reactance. Why? Because if you don't change the current at all, the inductor's not going to do anything. So it's a straight line with a slope of whatever your inductance is. Just draw a straight line. X sub L. Yes?
What if when the frequency is 0, what would XC be? You can't do that.
Well, it would actually be infinite if the frequency is 0, so we don't bother with that.
Like you can't divide by 0.
Well, actually, if you think about it, if you don't change the battery, once that capacitor charges, that's it. If you don't change the sign of the battery. So in other words, if you're never changing the voltage, which would be a frequency of 0, the capacitor is going to end up blocking everything. So in other words, if I had a battery in this circuit instead of this oscillator here, this would do it, the capacitor would charge, and then that's it. Yes?
When you say frequency, what are we talking about? Frequency of...
This is what we call angular frequency. Okay? Angular frequency. The frequency of your oscillator. Now, if you recall back to the generator, the generator clause. When we have an AC generator, we're usually rotating it in some magnetic field. We're rotating a magnet around a coil. That frequency that spins or that moves is going to generate the frequency of your current. So it's that frequency at which this is generated. That's what frequency we're talking about. What frequency we're trying to put through this circuit. Okay, so this is fine and dandy. But notice what happens in this equation here. What happens in this equation is that the inductor and the capacitor, the reactances here, really do subtract off each other. Because when one is positive, the other will be negative. So those voltages are going to subtract. So the reactances subtract off of each other. Well, what would happen if you ran the circuit there, where the two are equal to each other?
Isn't that resonance?
Yes, it is. It's okay. That's you paid attention in lab. Okay? This is your resonance frequency. This is the frequency at which it resonates. It just so happens to be the same frequency that they would go back and forth if there were just an inductor and a capacitor in a circuit. Remember, they would just go back and forth. That's the same frequency here. So in other words, anytime you get a resonance, you're basically trying to drive the circuit at the same frequency at which it naturally moves. That's where you get a resonance condition. When you're talking about a driven oscillator, and it would work with any driven oscillator, such as a swing. If you ever notice, if you want to swing higher and higher, you pump your legs in the same pattern each time you swing, so that forces that are going in there resonate with the natural frequency of the swing. If you started kicking your legs out at random places during the thing, it's not going to work. Or just imagine if you're trying to push somebody on your swing, and you first pushed him from one side, and then you ran up here, pushed him here, oh maybe push back here, push. That's not going to work. You want to push them from the same place every time, so that they go higher, 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 and then they scream, "Let me off!" Oh, sorry. That's what they do. All right, so this omega naught is equal to 1 over the square root of LC. And this, indeed, is referred to as your resonance. This is your resonance condition. Yes, the impedance ends up being just the resistance. Okay? So at this resonance, your impedance is just equal to the resistance. That's it. Because the other two things basically fight each other, cancel each other out at this particular frequency. You also have the phi equal to what? What's your phi going to be? 0. Because the two things are equal to each other. Notice that's a situation I didn't draw here. See? I drew the ones where the inductor was bigger, and I drew the ones where the capacitor was bigger. Well, there's a frequency in between where they're equal. And at that frequency, they just cancel each other out, and that's it. So when x sub L is equal to x sub C, they cancel each other out. Their total impedance goes right along that line there. You get a resonance. The other thing about the resonance is that then you also get your maximum power output of the circuit. Because remember, the power output depends on that angle phi. The average power is the IRMS V erms cos phi. Well, if the phi is 0, this factor is 1. So you get your maximum power output at resonance. So you get maximum RMS current, your maximum power output. So this is going to show you the power of an RLC circuit. And here's why. Because we can now have them adjustable so that we can actually allow particular frequency of current to go through and pretty much block everything else. And depending on the value of your resistor compared to the other ones, compared to your other circuit elements, as to how tightly you want that window to be where you're getting close to that resonance. There's a nice graph in your text, so I'm going to switch over there. Oh, okay, here's my zoom button here. There we go. Zoom some more. There we go. Lovely graphic placement. So this is your peak values, and they actually use different ones. They give you the voltage is 100 volts, that's your generator here. They give you an inductor and a capacitor, 2 henries and 0.5 microfarads. Those are pretty large, you know, but they wanted to make it so that it resonated at 1,000 radians per second there. So 1,000, you know, so they wanted to make the number nice, you know. It's about what is that? So 3, it's about 180 hertz, maybe a little bit less than that. They just wanted to make the number. So anyway, they made it so that this thing would resonate at 1,000 radians per second. And so then they show you that if you have 2,000 ohms as your resistor, you know, your resonance, it doesn't seem to really resonate that much. You know, because at all these frequencies, the 2,000 ohms is pretty much dominating your circuit. It's pretty large compared to what you're getting out of the inductor and the capacitor, unless you go to extremely large, you know, extremely small. So for a wide range of frequencies, you pretty much get the same current out of that circuit. But if you're able to tailor your resistor a little less, notice that there's a peak that starts to happen here. You start seeing noticeable changes right near the resonance. And of course, if you have a really low resistance, such as the 200, notice that that peak is very, very sharp and very, very high. So in a circuit like this, what you could say is you could say a cutoff, let's say 0.3 amps, and then cut off anything less than that, and then you're only looking at frequencies that are right around 1,000 hertz. That are right around 1,000 hertz. So why on earth would you use something like that? Well, there's one other thing that I would love to talk to you about in this class, but I don't understand it completely myself. That's why I keep looking it up. I keep looking up things about it as what's a nice, easy way to explain it. But I do know that one of the things that you can do is you can actually amplify a signal once you get it through this LC. So what we can do is we can have kind of a filter on a circuit. And so what we do is we take this thing, we say, okay, so this is old school, so I apologize, it's old school. So what we do is we have this right here, okay? We have a rod, and I'm going to take an inductor, put it here, and I'm going to take a capacitor and put it here, okay? Now, there's one thing about that capacitor I'm going to do is I'm going to vary that capacitor. Okay, so I'm going to make that a variable capacitor. I could also equally have a variable inductor as well. So I could have a variable inductor or a variable capacitor. So either one. So in this case, I'm going to make a variable capacitor here. And let's say that, and then this would go to an amplifier and into something else. So let's say that the inductor, I don't know, 0.2 millihenries, okay? 0.2 millihenries. Okay, now the frequency that I am trying to, and then I would go over here to my amplifier, I'd use a transistor, amplify this thing to an appreciable signal, because the signal is not going to be appreciable here. Not going to be appreciable coming out of here, just simply because it's not going to be appreciable when it gets to this rod. Anybody know what I'm talking about yet?
Car radio antenna?
Yeah, radio antenna. So let's say that I wanted to, the new alt 98.7, which used to be star 98.7. So, okay, operates at a frequency of 98.7 megahertz.
There's no capacitor, right?
No, the capacitor is variable.
Is that what that line?
That's what that line means. It's a I hope that line. Guys, electrical engineer, did I do that right to represent a variable capacitor? You don't know yet. Okay.
Yeah, haven't taken
This
it.
is supposed to be a variable capacitor. Okay. Hopefully I did that correctly to show that it's a variable capacitor. Please correct me when you go on, your electrical engineers, please correct me when you go on to advanced circuitry if this is wrong. Or come back and say, you were right if it's right. Okay, you see, you were right. Okay, so 98.7 megahertz. And so what I would do is when you adjust your radio dial, you're going to be adjusting one of these things, either the inductor or the capacitor. Cool, huh? You will adjust one of these until it resonates with this 98.7. So let's see what value the capacitor needs to be to resonate with alt 98.7. New alt 98.7. And of course, if you prefer to listen to K-Rock, which is now playing alternative music, because that's the new thing is to play alternative music, eventually enough stations will play alternative music that it won't be alternative anymore. And alternative will be Barry Manilow, because he won't be played anywhere except for, well, it'll be the alternative to the alternative.
Stations are measured in mega?
Yeah. You did. Oh, that's right, because you guys. Oh,
Satellite radio.
goodness. You guys are on satellite radio. You never use this dial. Oh my goodness. See, this is the fun thing. If I actually could go if I actually did cover chapter 32, I'd love to cover this stuff. There's just not time for it, but it's this kind of thing with the tuning circuit, okay? All right. Let me talk about radio waves here. Radio waves are actually electromagnetic waves, which we talk about in the next chapter. So they are the same in their form of light waves. And what is waving is the electric field. The electric field is going up and down as it moves at a particular frequency. And so it's that actually hits this rod antenna and moves up and down like this, causing the little current to flow in here at that particular frequency. Cool, huh? So in other words, the electric field comes along, it's waving along with the magnetic field. So here's the electric field. Okay? In other words, the rod antenna is going to couple to the electric field of the electromagnetic wave. And this is going to start pushing. That's why antennas are made out of metal. So they've got electrons in it. It's going to start pushing those electrons, up and down with a particular frequency. Now that's not very much of a signal. If you touch a rod antenna, you do not get shocked. That's not much of a signal at all. That's why you need the transistor to amplify. You need to amplify this once it gets through. But this part of the circuit picks out what frequency you're going to listen to. And if you notice that the FCC always regulates all these things, so like certain things can only be at certain frequencies, and certain things have to be so far apart. In other words, there isn't going to be a 9871 and a 9872 right here, because otherwise than that, they would be really literally competing with each other. And on AM stations, things get mixed up anyway. If you listen, we'll go over AM. Okay. I got 15 minutes. This is one problem. It's fine. Yes?
Is that why there's no even numbers?
Yes, that's why there's no even numbers. Because you want to make sure that it's at least so far apart, so that especially with your FM radio, Okay, so that's going to couple to this. So the radio waves are electromagnetic waves like this. Here we go. So I'll explain all this to you. So this is me going over chapter 32 without going over chapter 32, so we can spend next week more or less review it. Okay. All right. Because this is the cool part of chapter 32 that you guys would want to see about anyway. And you guys might actually be use at some point, especially if there's a zombie apocalypse and we lose all our satellite radios.
Who uses satellite radio, honestly? Auxiliary cords only.
All right, so we go. So the magnetic field actually waves like this. So this is my electric wave and a magnetic wave. And so they're waving back. This one, I'm trying to do a three-dimensional drawing here, so the one's waving up and down, the other's waving back and forth. Okay? Now, in terms of the radio waves that you get, there are two different ways to put a signal on this. Okay? In other words, the wave itself is not what you're listening to, because the wave itself would be a single wave of light. Okay? So if I have a wave, what I do is I want to add an electrical pulse to that wave. I want to add an electrical pulse to that wave. Then what happens is your tuning circuit resonates with what we call the carrier wave. The carrier wave is what you tune to. The electrical pulse is then what you end up hearing. So here you are at the radio station. Okay? Microphone turns this into electrical pulse, which is then added on to the carrier wave. And there's two different ways to add it. One different way to add it is to change the height of the wave at different points. The height of the wave. So in other words, your outgoing wave with the signal added on would look like this. Lower in some points, higher at other points, lower in some. I'm trying to keep this the same size and I messed it up. So anyway, so you're adding the up and down motion here. Now you're adding the up and down motion here. And this, by the way, is referred to as amplitude modulation, which we old folks called AM. So if you ever listen to AM radio, you're dealing with amplitude modulation. Now, amplitude modulation works at lower frequencies. We don't have to worry about make it really high frequencies. The frequencies here are measured in kilohertz. It's from 550 kilohertz up to about 1060 or something like that, or what's the highest thing on an AM? You don't know. Okay, somewhere at about 1060 kilohertz, which by the way is like about 1 megahertz. I don't know. It's
only 1060.
Yeah, for the AM. For the AM it is. For the AM. Now there's a problem with AM. Okay. AM has advantages and disadvantages. AM frequencies will bounce off of the atmosphere, which is great. Which is why at night, If you're listening to if you happen to be listening to an AM station at night, you can get things from Kalamazoo, New Orleans, all over the place, because the signal keeps bouncing around.
Wait.
Yeah. See, this is something that the sad thing is about. What we should do is we should make all college students, all engineers, get an AM, FM transistor radio, just get a transistor radio and start listening to AM stations and FM stations, and then you can learn all this cool stuff that was commonplace back in the 70s when I was starting to grow up.
And take it apart.
Wouldn't what you just said about the reflecting mean if I'm listening to like one station? Because sometimes I listen to 710 AM because that's the like.
And then other things crowded.
So I would like suddenly get something from.
You could get something from yes, it'll be crowded. That's why at night, if you're not close to a station at night, like if you're far away trying to listen to it, you'll hear things from other stations getting in. And here's another thing about AM. You're modifying the amplitude of the wave. Anything with an electric field, anything generating electric field is going to, near your radio, is going to modify the amplitude of that wave. So if you're ever listening to AM radio, so here's your assignment, okay? Go listening to some AM station that you never listened to ever before, whatever it is. There's some pretty Disney radios on AM, okay? Maybe, I don't know, Disney. And there's some, and all the rest of it I think is sports maybe, something to talk. So listen to some Laker game or whatever. Drive through McDonald's. Every time I drive through McDonald's on certain AM stations, especially those in the lower frequencies, the 510, the 5, I hear it. Why? Because whatever signals and electricity is going through a McDonald's is interfering with the radio signal that I'm getting. This also would be when they talk about static on the AM stations, because anytime there's a thunderstorm, lightning, 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 well, there goes the amplitude. You'd hear it on the radio. You could know that there's some thunderstorm because you'd hear on the AM. So the second thing that you do is to modify the frequency. Now the problem with modifying the frequency is you need the frequency of stations to be far enough apart so there's room to modify it. So there's room to modify that frequency, which is why the FM stations, have to have, there's no even numbers on your little FM dial because they all have to kind of at least give room so the other people can modify their frequency. The frequencies that you're modifying things by are in the order of thousands of hertz, because the order of your sound wave, whatever sound wave, 10,000, 20,000, which is okay because you're comparing it to megahertz, millions of hertz, which is why, again, you won't want to modify that frequency by some thousand of hertz because, well, it's going to shift it on the dial. If you try to do that, it's just not going to work. That's why you have to use a very large frequency to do your FM, to do your frequency modulation. So that's the second way of doing it, okay? Is to use the frequency modulation. I can't draw these waves worth nothing, so I'm not going to. So we get frequency modulation, which is your FM stations. It goes kind of like this. The waves stay the same amplitude if I could draw them correctly, but it works like this. So where you've got some closer together, some farther apart. Not this dramatic because otherwise then your radio wouldn't be able to take it up. So here's what happens. So the song is on the radio. Poker face, poker face. Okay, that signal gets added to here. Okay, so it gets added to your carrier wave. Here comes your carrier wave to your radio. Carrier wave. This sorts out the carrier wave. Your transistor, your circuit in here is going to amplify that sound. Take the electrical signal, turn it back into sound, and you hear poker face, poker face. Okay. All right. So now let's do to the problem itself. Okay. What do we do? Well, let's figure out what capacitance we need for this. Okay. Well, first of all, we want to calculate omega. Okay, which is 98.7 times 10 to the 6th. Let's go ahead and get that mega out of there. Multiplied by, what do I need to multiply by? To go from hertz to radians per second. What do I need to multiply by? 2 pi. Okay, so somebody please tell me what omega is. Okay, 6.2 times 10 to the n, that's close enough. And that's radians per second. And so we want our circuit then to resonate at this because we want this to be our resonance. So let's go ahead and put an omega naught here. And then we plug it into our formula for that resonance. So that 6.2 times 10 to the 8th radians per second is equal to 1 over the square root of the inductance, which is 0.2 millihenries, multiplied by the capacitance, which that's what we're looking for. Okay, so it takes some talent to solve for this thing. So what do we have to do? Square both sides. Woo! Somebody square that. Somebody already did square, didn't they? 3 point what? Okay. I'm not going to worry about units at this point. I've changed everything in the millihenries here. I've got to change that. Sorry. So it's 0.2 times 10 to the negative 3. And multiplied by my capacitance. Okay, so capacitance comes up here. 1 divided by 0.2 times 10 to the negative 3. 3.85 times 10 to the 17th. You're going to get a very, very small capacitor. But that's okay. Small capacitors are easy to make. To make a 1 farad capacitor, remember you have to pick a giant capacitor to do it. Or to have some specific design that won't run for anything over like 2 or 3 volts. What'd you get for this thing? Okay, 1.3 times 10 to the negative 14. I'll take your word for it because we're running out of time. Times 10 to the negative 14. Which is fine, and this is farads. So what we would call this, through, I don't know if you see any of this. I know picofarads has been, there's a lot of pico stuff. This one we call 13, here we go. Know what that is? Femtofarads. So we'd say 13 femtofarads for this number. 10 to the negative 13. 15. That's 10 to the negative 15. 10 to the negative 15. So in other words, I moved a decimal over 1 to make that negative 15 instead of negative 14 and then put my femto in there.
So in our cars, are we changing the capacitors?
You may be changing the capacitor, you may be changing the inductor. Okay?
Depending on the antenna.
No, just depending on the design of the radio inside of your car. You can design them with a variable inductor, or you can design it with a variable capacitor. One of them's fixed, you change the other one. I'll have to look up that.